Okay, sorry about that. My computer ran out of space. I've cleared some space and now I'm going to continue with the lecture. So the things that we were just talking about were different satellites, different resolutions temporally and spatially, and what they could be used for. So once again, if you look at an airplane, you could be doing a good job looking at canopy nutrients, species mapping. These higher resolution ICONOS WorldView 2 satellites that you have to task really can only take an image every year, maybe every month if you're lucky during a clear period. And things like MODIS sample at coarser resolution, but multiple times per day. And this can really start to answer some questions, whether you're looking at fire, species mapping, phenology. And so if we're looking at the Mire and looking at phenology, we would want to actually have something that measures multiple times per season, preferably every few days. And the problem with that is something like MODIS that could kind of answer that question really has such a coarse resolution that the whole Mire that's being studied would just be one pixel. The same kind of attitude or kind of concept can be applied to other disciplines. So if we look at archaeology, when they use remote sensing, there are different reasons that they would use it, and different satellites or platforms come into play. So you could have ground penetrating radar, which you can do every day. That's easy to do, but expensive, but you can get 1 centimeter resolution. Something like AVHR, which stands for the Advanced High Resolution, actually it's AVHRR, Advanced Very High Resolution Radiometer, really is coarse. It was developed in the 80s, and that tends to be on the order of 1 kilometer to 10 kilometers. Super, super coarse. So if you're looking at individual sites where you're trying to find sites, aircraft and drones are helpful. If you're trying to look at how these sites link together, something like Landsat could come into play. And if you're trying to link past societies with current processes that are going on, you want to use something that actually gives you kind of this kind of phenology or temporal sequence across the landscape. So once again, if we talk about resolution, we can also have spectral resolution. So Landsat's been around. Landsat, the first Landsat in the 70s had basically, I think, a few bands. As they got better, they had more bands. Hyperion was a experimental satellite by NASA that ran for about 6 years, and it divided the electromagnetic spectrum that we were interested in into 244 individual slivers. So just think of that. Each pixel has 244 different values representing anything from little slivers of blue all the way into the shortwave infrared. And it could tell you a lot about the characteristics of the landscape. Temporal sequence is of interest because you, once again, want some things that go over multiple times. If you're doing atmospheric studies, you want something that's hourly. And so there's actually these satellites called GOES, and they're geostationary. They stay over one part of the planet, and they just measure that aspect of the planet. And the newer ones measure every 15 minutes. So you can actually see the moisture and cloud circulation on the planet. And this is used for a lot of meteorological work. And once again, ICONOS and WorldView 2, you have to task. So depending on how much money you have or how often you need that image, you might decide to use that satellite. So once again, temporal resolution is the repeat time to acquire data. Sometimes you only need it once, but really, usually you need it multiple times. Radiometric is how divided the sensor is into kind of separating or how sensitive. If you think about music, you might have heard of chiptunes or 8-bit music. So early video games had a kind of really coarse synthesizer in it. That recorded at 8-bit resolution, meaning that the volume was only 8 bits of values. Now CD quality is at 16 bits, and when they record high resolution digital imagery in a recording studio, they measure at 96 bits. So really high, minute changes in the volume. Sorry, they actually measure at 32 bit. Sorry about that. The temporal resolution is a little different here with ICONOS, depending on your latitude, because the orbital paths converge because it is a polar orbiting satellite. You'll find that the ICONOS image has a better repeat time when you get closer to the poles because the flight paths overlap. And so you're more likely to get coverage easily there or repeat times. And things change quickly. So if you're trying to do something where you only get one view per month, so Landsat flies over about every 14 days. If one of those is cloudy, you might miss that month or miss that day. So if we look at February, March 2015, this is the Great Bay. Durham's up here somewhere. You can see that this is snow on the ground. So these kind of bluish areas are the fields. You can see Pease Air Force Base right down here. If we look at the best Landsat image from March to April 2015, you only see clouds. So this, I had a thing to delete this slide, but I actually think it's good to keep in. If we look at May, there's no snow on the ground. You're seeing things starting to green up. You can see the forest kind of look green. Some of the bare grass or ground looks a little brown, so it's kind of starting to green up. May to June, if we have a nice clear shot, you can actually start to see bud break throughout this. But maybe bud break happened a little earlier than when we got this image, which was probably May 21st. And then in the height of the summer, you have kind of full leaf, and it's really kind of a nice green, lush forest across the New England seacoast region. So the time periods of collection are also of interest. So if you're trying to look at the past of, let's say, Stordahl and Meyer, you know that you can look at Landsat that started in 1973. It's going to be really coarse, but you can actually start to see collections around the world. And then these Landsats have continued. Some of them have overlapped kind of their lifespan. Right now we have Landsat 8 flying and is collecting data. And we also have Landsat 7, which is having some problems. That's a very technical issue. But Landsat 2 and 5 and 3 are done. The Landsat 6 blew up on launching, so never was able to make it to space. MODIS we know goes back to 2000. There's also some other things that ran for about 6 years and lasers burned out, so they were only up there for 6 years. So this continuation of data sets is really important for NASA and Earth and environmental science. So if we look at the different Landsats, you can see 1, 2, and 3 had some lifespan. There was some overlap there. Landsat 5 was the longest running. It was decommissioned in 2013. Landsat 6 blew up, trying to reach orbit. Landsat 7's going. Landsat 8 started in 2013 and is continuing. This is an older slide. And Landsat 9 should, I believe, launch this September, which will be quite exciting. So there's the other thing is that sometimes there's correcting the imagery. So radiometric correction is dealing with different sensors and different satellites that might have kind of measured and have different kind of time periods of sensitivity. There's the look angle that needs to be corrected. So if you're looking at an angle through the atmosphere, you're having a thicker atmosphere that can kind of contaminate the imagery. And also if you're looking at, Landsat 5 and Landsat 7 or 8, they have different kind of radiometric values that you need to kind of correct for. The other thing is orthorectification. So knowing where you are on the planet is important. These satellites can only get so good. So sometimes you have to kind of move them around to where they are on the planet. That's gotten much better with more modern GPS. And also there's the influence of landscape. So if you're in a mountainous region where they don't really know a good topography, that's going to warp and have some kind of angle issues with your imagery. These are things that you sometimes get when you get into your second remote sensing course, but they should be something that you know about when you're working. I had mentioned a polar orbiting satellite. So things like MODIS, Landsat, and most of the satellites that want to kind of get a clean shot at the brightest point of the day tend to be polar orbiting. These tend to kind of fly over the pole, come down, fly over the South Pole, and come back around. And they move almost with the turning of the Earth. So MODIS, the Terra satellite in the MODIS platform, takes a picture at 10 a.m. Aqua follows and takes a picture at 2 p.m. And so that's kind of the collection of MODIS. A geosynchronous satellite is basically using the momentum of of the satellite and the gravitational pull of the Earth to kind of keep it in the same orbit. And so they always focus on the same area of the planet, and they actually have to be located over the equator. And so these are really good to kind of get continuous imagery of one area. And so these tend to be the GOES geostationary satellites that monitor the environment and meteorological phenomena. The newest one collects imagery every 15 minutes and also does a really good job of collecting information about lightning strikes. The other thing to think about with remote sensing sensors is whether it's active or passive. So an active sensor is like the flash on a camera or your phone. It basically sends out light which reflect off the object and come back. Or passive, you're just using the sun or the ambient room light to take your image. The good thing about passive is it doesn't take a lot of energy. You're just using kind of light reflective things, opening up kind of the shutter and collecting that information. An active sensor shoots radar or lasers down on the planet and they bounce back, and that is what kind of images the Earth. And so for radar and LiDAR, as I get into them, they're really unique kind of aspects of remote sensing. So once again, passive tends to be most of what we talk about or you see when you look at Google Earth. They tend to be airborne imagery or QuickBird or MODIS or Landsat. These are satellites that measure usually in the visual range and into the near infrared and shortwave infrared. As I mentioned, LiDAR is basically a light that's emitted, a pulsed laser that measures the distance to something as it bounces back. So it knows the time that laser takes to go there and back. And that can give you three-dimensional information about the planet, both if you're looking at the forest, topography, or even the shape of the Earth, because the Earth is not a perfect sphere. This is a really powerful thing because some of these laser pulses, if flown on an airplane or drones, can actually penetrate canopies, and you can see the underlying kind of structure of the forest. You can see the topography under the canopy as well as canopy characteristics. Radar is a little more complicated. There are different wavelengths of radar that are sent out, and how that interacts with an object tells you aspects of that object. So LiDAR is an active remote sensing technique. The light reflects off branches, leaves, or the ground, and as it returns, it gives you an idea. So if we look at laser illumination here, you can see that if we kind of sum what would be in this area of this tree, you can see that you have information about the ground, understory, maybe the first kind of canopy position, and then you have a leading edge. And these are really good aspects for understanding forest structure. There's been a few satellite-based LiDAR. The first one was called GLASS. It was on the ISAT, and it was really devised to measure the ice sheets. But because it was flying over forest, it was also used to kind of quantify or understand forest structure. Higher resolution, so this is an image of a forest in La Selva, Costa Rica. You can see a footpath here, but you get kind of information about tree canopies. So the brighter the image, the higher the kind of vegetation is there. So you can see a gap here with possibly palms in here. And this really gets powerful when you're trying to understand kind of forest structure. You can even get higher resolution, and this is a remote sensing technique called terrestrial laser systems. And this is a laser that's placed kind of on the ground on a tripod, and it shoots lasers all around. And this is about 400 million laser shots that are collected. So the brighter red means that the object is closer, and the further away it is, it turns into kind of the violet into the purple. What's interesting here is the top is Harvard Forest. The bottom here is La Selva, Costa Rica. This is work that we've done in both places with a terrestrial LiDAR system. You can really see different forest structure. This is so fine-tuned that if you were to zoom in some of these leaves, you can see small ants or mushrooms growing on them. It's a powerful technique that is limited in the spatial coverage. So this is basically covering a understanding of a 30-meter radial plot. You can also put LiDAR on drones. So this is Frankie Sullivan that works with our group, and he's getting ready to fly our drone off the Harvard forest tower. So this is indication of his confidence in the sense that he is taking off from an 80-foot kind of tower and landing a drone that's about $80,000. You can also use airborne LiDAR to look at forest structure, but also snow. So we've been doing studies where we measure snow depth. We fly with no snow, and then we fly during the winter season when there's been snowfall, and we can estimate shallow snow depth, which is pretty cool. So here at Thompson Farm, which is nearby, you can see that we've been able to measure deeper snow, which tended to be here in the field, possibly blown there, while areas of the forest here tended to have lower snow. That could be canopy interception, but also some of our error. You can see that we're really sure in the fields of our estimate of snow depth, and kind of uncertain in areas that have less LiDAR hits of the ground. And that's because the canopy is intercepting it. Me as kind of working in forest carbon dynamics, I'm really interested in the forest structure. But here the forest structure is messing with our ability to kind of quantify snow depth. So here's another aspect of using LiDAR to measure snowpack and its spatial structure, and where there is deep snow and when there is more shallow snow. We've also worked in the tropics with airborne LiDAR. So this is a gap in Tapajos National Forest. You can see small palm trees here in this gap. And my original work for my PhD dissertation was to write algorithms that kind of find the edges of these trees and count them. So we did have one person who actually took 2 weeks and measured individual trees. And what we could do is we could do this, we could do 20,000 kilometers in a matter of a few days compared to them doing 2 weeks with just 1 kilometer. So this terrestrial-based LiDAR system is helpful for understanding aspects of forest structure. So once again, this is downsampled from the 40 million coordinates that we got from where the terrestrial laser scanned. Once again, Harvard Forest and Costa Rica. A newer satellite that's airborne, that's laser, is ISAT-2. Exciting name. They had ISAT-1, they named the second one 2. This shoots about 6 laser beams constantly across the planet. So here we're looking at Antarctica. These are the tracks as it goes over the poles. The reason why it avoids the pole is not because there's an alien kind of landing pad there. It's actually, they need to be a little off center to kind of capture and do their kind of angled polar orbit of the planet. So these are the heights. Red is a higher elevation. Blue is a lower elevation. They're able to interpolate this and get information about ice sheets and the depth of ice sheets and how these change as well. So if we're looking at Antarctica here or Greenland, you can see on the edges here, there is rapid loss of ice and glaciers. There's some accumulation here in parts of Antarctica, but really you can start to quantify the loss of glacial ice. This is what ISAT-2 looks like. It has the 6 lasers that shoot around down. They're active and they measure the landscape. What's interesting is it doesn't really shoot them down. It actually measures the return pulses, and it's actually called a Geiger LiDAR. It's so sensitive, it's actually measuring individual photons. And so this is one track over about 2 kilometers. And so you can see that orange is finding the ground. Green tends to be some additional vegetation. This is in the boreal forest of Alaska. Here you can start to see some kind of mid canopy, upper canopy. So this is really important. And sorry, this is a 400 meter, not 4 kilometer segment. So within 4 kilometers, you can get kind of a pretty interesting forest structure estimate. If we're looking at New England here, we can look at this one track of ISAT-2. You can see that we've mapped it along with a digital elevation map and also land cover of the different forest types. And you can see that north-facing slopes tend to have more kind of dark green evergreen forest, and then these other ones tend to have mixed and deciduous forest. RADAR stands for radar detection and ranging. So it basically shoots radiometric data down, and it bounces back. And as it's scattered, it tells you aspects. So if you have a radar called X-band at 3 centimeters, it's only going to penetrate a little bit into the canopy and reflect back. So it can give you kind of the upper canopy height and overall kind of attributes. Longer wavelength, like this L-band, come in and actually can hit the ground and give you good topography. And if you look at kind of the C-band, this plant soil kind of combination comes into play. Radar is really complicated. I tend to use only products that someone else has developed, but it is a really interesting aspect of remote sensing. The reason why they're called X, L, and C-band is left over from World War II, I believe, and the development of some of the radar technology. So there are a lot of satellites that are Earth observing that are being developed by different countries around the planet, from Indonesia to Nigeria to Belarus, Japan. These are all really interesting because a lot of this data can be used by the international scientific community to better understand the planet. So South Korea, Turkey, everyone's developing really interesting kind of combinations of satellites. So this is NASA's suite of upcoming satellites, at least in the past. You can see that we have Landsat 7, 1999. You have Aquaterra, the MODIS group from 1999 and 2002. And then you have the Global Precipitation mission. You have all these interesting satellites that are Earth observing, and you have many more coming up in the future. I like to sometimes talk about the crazier satellites. So the GRACE gravity recovery experiment is really interesting because it actually doesn't image the Earth. It looks at the gravitational kind of pull of the planet to understand what's going on. So it's basically 2 small kind of train car satellites. One flies, the other one flies behind it, and it measures the distance between the two using a laser. So kind of just a single beam of laser. And when the first one gets pulled further ahead, it means it's going over an area of greater gravity, and then the other one catches up. Doing this many times, you can look at kind of some geotectonic activity, big landslides. You can even look at kind of water in a system. They've looked at the depletion of water in India, in the aquifers. And here you can look at the seasonal water change in the Amazon. I mentioned GOES as a geostationary satellite, and this parks up there and looks at water vapor and as a gas in the atmosphere. And it's really important for understanding kind of global meteorological phenomena. The Tropical Rainfall Measuring Mission is a combination of radar as well as a suite of observations across the planet. And this looks at the Intertropical Convergence Zone. You can see it right here. And as the planet tilts seasonally, it moves up and down and changes the rainfall patterns on the planet. There's also a thing called the A-Train, which is fun to talk about. These are satellites that follow one after another. So the first one goes over is Aurora. Then you have CloudSat, Calypso, Aqua, which is part of the MODIS collection. There's some other remote sensing platforms that are up there that are actually placed on the International Space Station. So EcoStress is one that looks at just temperature, and it looks at the temperature of the landscape or water and gives you information about how that changes. The cool thing about EcoStress is because it's on the International Space Station, its orbital pathway is not always tied at 10 a.m. or 2 p.m. And so you can actually look at some diurnal vegetation water stress across the planet. Another sensor is called JEDI. This is their little "May the Force be with you." But JEDI stands for the Global Ecosystem Demography Instrument. It's a LiDAR instrument that is on the International Space Station, and it takes images in 3D structure of the Earth, mainly forests, to really understand carbon dynamics and hopefully water cycling. So that's on an experimental 2-year mission, but they're extending it because it's been pretty fruitful. So over the next 15 years, about 30 space agencies are going to develop about 760 new sensors on these Earth observing satellites. It's amazing. It's a great time for Earth observing and remote sensing. And a lot of these are being repeated in series to continue the temporal aspects of remote sensing. So I've talked a lot about satellites, but I really want to talk a little bit about airborne and talk about Stordalen-Meyer and the ability to kind of remotely sense vegetation at Stordalen-Meyer and what you might want to find out. So it's not always the big expensive. Sometimes you can do it by kite, airborne with an airplane, and sometimes you can even stick it up on kind of a crane and do imagery that way. So let's talk about some examples. When you're doing remote sensing, you need to think about what information you want, how much detail, and what type of detail. These start to get at the questions you want as a scientist. So knowing that many of you are not going to be geospatial or remote sensing experts, but knowing what you need and portraying that to a remote sensing kind of specialist or scientist can really get at what aspects of the remotely sensed data you need. So sometimes you can just put it up on a crane. Sometimes you can put it on balloons, and sometimes you can put it on airplanes. And so these are really important. So think about, you know, using these and kind of quantitative applications. There is some historical data, as I mentioned, that Corona spy satellite, they've declassified that data. So we're starting to look at burn patterns in the Amazon from the early 60s that have never been able to be looked at before because of the declassification of that data. So there's more and more commercial applications for water resource management and for agricultural management. But there's limitations, and we can talk a little bit about the limitations. It has a lot of different issues. It's expensive. So if you're putting up a satellite, they cost anywhere between 100 million and close to probably $1 billion. And that's a lot of money. Drones are a little cheaper, but they still can be expensive. Technically, it can be difficult. One of the best things that NASA did was it actually started to create products using the MODIS data. So scientists could get the leaf area index developed by MODIS, or what time of year a pixel burned, or estimates of FPAR and things like that. These are really useful because they were kind of done by the experts, the physical, physicists that are involved with remote sensing. And then these products were easily used by other scientists. So once again, it's also not directly measuring it. There's a lot of complications when you're looking at remotely sensed data. So you're measuring a surrogate of the vegetation. So reflectance and brightness temperature are estimates of what's going on the forest. And you need to relate this to other direct properties that you measure on the ground. That's why when we work at Stordalen-Meyer and we fly our drones or we look at satellite imagery, we're still going down and doing vegetation plots and knowing exactly where those vegetation plots, because then we can relate that vegetation species, property of that vegetation with the remotely sensed data. So if you look at a satellite like Landsat 8, you can see when it was launched. You can see that it's sun synchronous orbit. So it's a polar sun synchronous. So it's trying to fly and stay with the sun as the Earth turns. Circles the Earth every 98.9 minutes. It crosses the equator around 10 a.m. taking its pictures. And these are the different bands on the new Landsat 8. So there's 11 different bands. So as I said, that kind of the remote sensing is a surrogate for vegetation. There are a lot of indices or vegetation indices that try to tease out information about the vegetation you're looking at. Two of these are NDVI and EVI, so the Enhanced Vegetation Index and the Normalized Difference Vegetation Index. These are band proportions and they're normalized, so the difference between near infrared minus red divided by near infrared plus red gives you a value anywhere between -1 and 1. And these give you information about the properties on the planet. So snow would reflect lots of light, and so it would have a different NDVI. But if we look at healthy vegetation, you have about 50% of the light reflected in the near infrared, 8% in the red. If you add those together, you get 0.72. If vegetation starts to experience drought or is unhealthy or disease, you actually start to have more reflected in the red band and a little less actually reflected in the near infrared. And this gives you an indication of that plant health. But this changes between species, seasonally it changes. So NDVI is a surrogate for a lot of different things when you're understanding vegetation indices. Here's a close-up of it if you wanted to see what's going on, but it's a nice diagram to show you how these two kind of bands, red and near infrared, change to give you an understanding of forest health or drought stress. So if we think about what we're looking at, I like to put this in here. Things don't always seem to be what they are. So here is some work by Andy Goldsworthy. He's a landscape artist that does kind of temporal installations. He takes a picture and then they often fall apart. A really amazing artist. But he did this thing called pools of light, which is really interesting. So he basically collected a bunch of trees that fell during a storm, and he changed these logs in a way that by looking at it on one side and then moving around to the other, you saw something completely different. And it's basically a dark and a bright circle in an area. And so if you look at early morning and evening from the same position, you can see that the properties of light reflecting off this really change what you're seeing. It's not painted or anything, it's just the angle of the light hitting the wood. If you walk all the way around it, it's really interesting because it actually starts to change color as you move to the other side. And so really what's going on here is that depending on what you're looking at, you need to understand the properties of the object you're looking at. So, and this can be true here. So we see this nice checkerboard pattern, and it's really trees that were felled in a kind of checkerboard pattern in Idaho. So once you collect your data, there's a few types of analyses you might do. And I'll just go over these real quickly, but these are what you start to do when you have the data and you want to understand the vegetation. So you can classify it. You break the object into distinct groups. You look at the image and say, that's water, that's a tree, that's a house, that's a field, that's a road. So those are different classes. And so you have this raster image of all these little pixels, and those pixels are assigned a value that's distinct for that group. You can also compile values and look at how these change with different locations. So what are the values in a forest versus a field, or between a forest and this other forest? You can also look at continuous variable estimation. So if you have temperature on a lake and you can look at temperature through time of the lake, that gives you information about the continuous variable. If you're using LiDAR, that's really interesting because you can look at canopy height, which is a continuous variable, or aspects of the canopy as you move through the canopy, the kind of canopy profile. You can also look at temporal changes. Now, these temporal changes could be different classes that arise. So it was a forest, now it's a field, now it's a suburban home. You could look at disturbances in a forest as a forest, then a gap or a tree fall, secondary growth, and then it comes back into a full forest. And so that disturbance kind of process is really interesting to people looking at forest carbon dynamics. And then you can also use some of these values to drive models or parameterize models. So if you have some sort of model, and we talk about DNDC with some of Ruth's work at Stordalen, but also the new ecosystem model, these values such as water table, possibly estimates of biomass, can be fed into the model to better simulate the processes going on in the ecosystem. Once again, classification assigns different groups. The level is called a class, and these can be based on the spectral signatures defined from those features. There's 4 major methods for continuous variable estimation. You can have parametric regressions, non-parametric regressions, physically based models, and a hybrid method of all of those. A remote sensing class will go into these different methods and how to use them to understand the environment, but we're not going to do that here. So when you're looking at remote sensing, you need to consider the temporal, spatial, spectral resolution that are available with that data. what needs to be done to process it, what others have done. So I'm one for not inventing something new if someone's done a good job with creating a product or some remote sensing kind of algorithm, and I try to understand what others have done. So sometimes if other people haven't done this, it could be because it's difficult, but it could be a new avenue for you to pursue in remote sensing science. So really think about the question you're trying to address as a scientist, where and when you're interested. Is satellite data available? Does the satellite provide the estimate of a continuous variable maybe that you want? What has been done previously? So you'll find that there's been a lot of great work previously. And then what new method or new algorithm can you apply? And this could be either a new method in an area that's already been studied, or taking a previously used algorithm and applying it to a new region. So for our work at Stordalen, we've collected imagery over 6 years. We missed 2019 isn't here, but we have that processed. 2020 we missed due to COVID, but right now we have Sophie Burke, who's a postdoc with our group, and she's collecting drone imagery right now. So by the time of eMERGE, we'll have many years of drone data. This is just a little fixed wing styrofoam plane that has a camera that we bought at Best Buy. And it does a great job collecting. So not to get into the remote sensing aspect of this, but these are 700 images that are collected from the drone. We stitch them together. We then decide where they are on the landscape, and we can actually look at this change over time. So we have a 2018 paper where we classified using a neural network. So we used information continuous values of the red, green, and blue, and also a thing called texture analysis, which looked at the pixels next to the other pixels, so kind of the bumpiness. And we were able to use a neural network to classify it as multiple vegetation cover types, open water, rock, and other, which was human boardwalks and research shacks. So right now we've been using a hyperspectral drone to look at cyanobacteria in New England. And we've also been flying this hyperspectral drone on forests at Thompson Farm and Harvard Forest. And this starts to divide light into little slivers. And it's a really exciting method to quantify vegetation. And we're hoping to fly this next summer at Stordalen Meier. So if we look at snow, these are different plots. You can see the signature of snow is very different. It reflects a lot of kind of lower light here and not much there. If we look at cyanobacteria, excuse me, you can see that the different kind of chlorophyll A or kind of sediment in the water changes the spectral signature. And this really gets at the kind of quantifying and estimating chlorophyll A or cyanobacteria in these lakes. For work on the tundra, Sophie Burke, Clarice Perryman, and Frankie Sullivan collected hyperspectral up in northern Canada. And we've been able to tease out the difference between fens, new or young bogs, intermediate, old, and different types of pulsa. And they really have distinct kind of reflective properties looking at the hyperspectral sensor. So this is a hyperspectral on a drone that has about a 3 centimeter resolution that can really define attributes of the landscape. So this is what they look like if we look at a kind of a true color image. So on the left is Lutos, on the right is Wrigley. You can see basically the boardwalk there and the type of fen that it is. We've been using this data and bringing it into Google Earth Engine to both quantify the classes of vegetation, but actually look at species percentages. So this is looking at sphagnum moss and the percentage of sphagnum moss between 0 and 81% in each pixel. And so you can see that we're getting actually pretty good values and ability to quantify species using the hyperspectral imagery. The same model then applied to Apex Beta, which in Alaska didn't blow up. We're excited about that and does a pretty good job estimating sphagnum moss there as well. So our future work at Stordalen, as some of you are involved with the eMERGE Institute, is we will be flying our hyperspectral instrument in the summer of 2022, not 21 due to some COVID issues. We're hoping to look at vegetation chemical concentrations and try to relate that using the hyperspectral data. We're also going to try to identify plant functional groups. So these plant functional groups will allow us to kind of provide data for the ecosystem model. We will be looking at focal areas. So if people are doing some research projects in the future, and getting those focal areas within our kind of flight domain would be helpful. So we're also going to continue kind of a fixed wing approach that we've done in the past, continuing this data collection. What's interesting is Sophie, who's flying right now, is flying a new drone that has a red, blue, green sensor on it, but also has a red edge, which is right as it goes up into the, and then also a shortwave, or sorry, near infrared. And we're hoping that this is a 5-band remote sensing sensor that will really provide enough data for vegetation analysis. What's cool about her sensor is it's cheap, it's easily deployable, and could be flown multiple times without kind of swamping us with too much data. So one day of flying our hyperspectral kind of drone, we get about 50 gigabytes of data once it's processed. So some other work that we hope could happen is we do have a LiDAR on a drone, and here it is at Thompson Farm, flown over a forest and two types of forest in that field. And we're thinking that this might be a good way to look at the topography and the permafrost collapse at Stordalen-Meyer. We're also going to do a thing called structure from motion, which basically takes kind of just images taken from 2 different directions and gives you a topography. And so that is there's a whole nother new avenue of remote sensing that's really interesting. Basically using cheaper images that overlap and have similar points from different angles to understand 3 dimensions of that object. So just to talk about the power of temporal remote sensing, here we have 6 years of our data focused in one area of Stordalen-Meyer. 2014 was pretty dry. 2015 was dry, but you can start to see some of this collapse. 2016 started to get a little wetter. You see these thaw ponds really starting to come into play. Here you see the thaw pond starting to fill in with some sort of the grasses and carex, and that's really kind of a different vegetation. You see the more of that kind of grassy vegetation moving in with new thaw ponds moving up here. And here you have 2019, which is a little drier, but also changes and permafrost collapse. And this is the area that kind of continually measuring an area over time with a drone is really exciting. The problem is we only have 1 image per year. So our temporal resolution is once per year. Really, we fly about 3 times every field season when we're there, but we pick the best one. And we always try to get closest to around June 20th, 24th. That's kind of our target area. The next steps would be to fly the drone multiple times over the season. And I know that Sophie Burke has done this with thaw ponds, where she's flown the drone every 3 to 5 days to look at the thaw pond changing with precipitation and other dynamics of the season. So that's it for the remote sensing summary. I know this was short and was interrupted by cicadas and my computer not having enough room to store the whole lecture. But please email me if you have any questions, and I'll be part of eMERGE and the eMERGE Institute in the future. And I'm happy to try to help out if anyone has any research questions. Thanks a lot. Bye.